Okay, so we're going to talk about geometric attributes for, I don't know, maybe 20 videos. Let's start with the basics. We're going to talk about what dip is. So dip is exactly what a geologist would think it is. We're kind of placing the marble on a tilted table, and we're going to see what direction the marble rolls. Azimuth is the direction relative to north that it rolls. So let's look at some videos or some slides and get started with dip azimuth and dip magnitude. All right, so this is how we calculate it in AASPI. You can see we start with the seismic amplitude, and then we run a similarity volume so that we can calculate dip off of that similarity volume. And we calculate it in both the inline and the cross-line direction of the dip. We have our confidence of the dip is another good output seismic attribute to look at. And from the inline and the cross-line dip, we can calculate the dip magnitude and the dip azimuth. And so the way this works is typically you have to have some sort of kind of filtered window, like whether you're working, in a circular window and looking at those within that range, that radius range, or if you're calculating so many in the inline and cross-line direction. And so most algorithms work one of these ways, letting you choose how many neighboring wiggles you want to compare it to. All right, so let's talk about how we calculate dip. In AASPI, we have a couple of different methods to do it. Gradient structure tensor is one of them, so GST, and then semblance search. And I'm going to try to go through those really quickly because I'm trying to keep these videos at less than 10 minutes. So we'll start with gradient structure tensor. In this case, what you're trying to do, let me do it with like an analog. So imagine that you're kind of running your hand over a rippled surface. Okay, maybe it's some nice outcrop with those ripple marks. And so your brain's kind of detecting which way the surface is sloping by feeling how it changes in different directions. That's kind of the similar way that the gradient structure tensor works. So at each point in the seismic volume, GST is measuring how quickly the seismic amplitude changes in all directions. So you're kind of feeling out the steepness of that slope. And so the way it technically works is by creating a matrix that captures the rate of change. And you can kind of see that here in this image. But we're going to look at it in three different directions, both the inline, the cross-line, and then also kind of vertically. So it looks more complex than it is intuitively. Semblance search, in this case, you're trying to stack things together. So you could think about it like if you have a bunch of accordion papers, you'd kind of tilt them until the pattern lines up just right. And so this is the way the semblance search works. It's a little simpler to run, like algorithmically less complex, so it'll run quicker. And it's kind of thinking about it in terms of like, okay, well, if we tilt everything in this window at this angle, will things line up? So it's kind of thinking about it that way. And so it runs through a bunch of different test angles, trying to see how well things line up. So it's measuring the semblance of it. So you can imagine, oh wait, I've got this animated. So you can imagine we're going from -20, and then every few degrees we're calculating it. We're calculating the semblance on each of those. So how similar are the wiggles? And you can see we don't have great semblance or coherence right now. But eventually we're getting a dip that has the maximum coherence. And so that's the one we would end up choosing to use in the semblance search. So there's, this is kind of just a summary of some of the basic features that you're going to see in each GST and semblance search, just so you could go back and look at them later. And this is absolutely not my best slide, so I'm going to have to change it later so that you can actually read it. But it's just kind of a comparison and contrast of GST and semblance search. Looking at some of the advantages. One thing that could help you run things quicker is to be kind of smart and intelligent about your search range. So if you're not expecting 30-degree angles, then dips, then don't search for those. So let's look at some real-world applications. Here we're looking at an inline dip component of a time slice. And so there's some interesting lineations. We could see that the dip goes from -15, which is darker in color, to +15, particularly on the lower right-hand side of this image. There's some interesting features. And if we look at the cross-line dip, it looks a little bit different. So let me go back and forth between the two. So we've got cross-line, inline, cross-line, inline. So you can see that the direction that you're calculating dip really kind of matters and shows you different features. We can also look at the dip azimuth. So what direction relative to north, so 0 degrees is north, or that blue, is the seismic dipping. And so here we're looking at the dip azimuth, and this uses a balance of the inline and crossline dip calculations. So we can see we've got some features here in green that are kind of dipping at negative 120 degrees, so maybe to the southwest, if I've got that right. The yellower one here, that one's dipping more towards the south. These purplish ones are dipping a little bit more towards the north. You can co-render that with the magnitude, so how much is the dipping, so how strong is the dip, and in that case we often use a overlay, like a grayscale overlay, where we only select the black to be opaque and everything else is transparent. So some cool figures. You could also look at it in vertical section, which gives you a lot of information. We've got some really great, this is in the Great South Basin, so there's some amazing polygonal faults and interesting fault features going on here. And then here's another display. I'm pointing out with the green arrows some really lovely cliniforms. So you're even picking up some stratigraphic layers. And then here we can kind of move past just looking at inline and crossline dip, and we could look at apparent dip. So in this case, we can look at it in any direction. So 0 degrees, which would be the inline in this case, in the upper left-hand side. We've got 30 degrees at that time, 60 degrees, 90 degrees. And so you can notice how these lineations drastically change depending on the direction in which you're running the calculation. I mentioned you should also be able to calculate confidence of your dip. So in this case, where you see our confidence intervals, where the whiter colors are, we're really confident in that dip calculation. The grayer, blacker colors are areas where it's a little bit noisy and maybe the algorithm didn't have quite as much confidence. Just a few more kind of moving down deeper in the survey. And then here's a nice co-rendered dip azimuth, dip magnitude section that gives you a lot of information. I always find we don't think about dip azimuth and dip magnitude as much as we should, but it really helps reveal a lot of the geometry that's quite important. And then just to kind of like recap, I tried to think about what are my main points. So dip attributes are really great to use as they help you understand the geometry. So subtle faults can show up quite well on these if you don't have super noisy data. And other things that you could kind of keep in mind is that the dip and azimuth are calculated from the seismic volumes, so they're not providing that true dip. So we're typically working in time data. So you always want to keep in mind those pesky but interesting velocity variations. And QC control is very important. So like I always say, the more you could clean up your data, the better, the better to do that. So you can have higher confidence in areas where you have the strong reflectors. We'll often see that. You want to watch out for artifacts near faults. One of my students has been doing a project on the noise near faults. And so those are something that could pop up in issues with dip calculations. You want to make sure that you're getting reasonable dip ranges. So as geophysicists, we always want to kind of go along and make sure things make sense with geology.